Welcome to the video on Euler's method. So Euler's method is a method for solving differential equations when given a derivative and an initial value by using tangent line approximations. So for example, if we were given an initial point of 0, 1, and our derivative was something along the lines of 3x plus y, then we could find our slope at that point, which you'd plug in 0 here and 1 here. So that would give us a slope of 1. And then you can approximate your next value. So if we were doing a step of 1, so if h equals 1, then our next x value would be 1. And we can find our y value, our next y value, by taking our previous y value plus our step, which is 1, times the value of the derivative at that point. So to figure out what goes into this box here, you would take yn plus 1 and say that equals y sub n, so your previous one, which was 1, plus your step, which is 1, times the slope, which was also 1. So 1 plus 1, which is 2. So then your value would be 2 here, and then you could figure out the derivative at that point. So you would have 3 times 1 plus y, which was 2, so that's going to equal 5. So your slope is 5 there. So then your next one, your yn plus 1, we'll use 2 for x. So then we have y sub n, which is your previous one. So our previous y was 2, plus our step times the previous slope, so times 5. So this equals 2 plus 5, which is 7. So then our new y value is 7. We could find the next derivative and then keep going and figure out all of these approximations. So here we have an IB practice question relating to that information. So it says, given the derivative dy dx equals 2x plus y and the initial point of 0, 1, use Euler's method with a step of 1 to approximate y when x equals 3 and when x equals 5. So we'll draw our table. We have x, y, and dy dx at those points. We have an initial point at 0, 1, and we want to find y when x is 3 and 5, and we have a step of 1. So we'll have 1, 2, 3, 4, 5. And we want to find this value here and this value here. So dy dx equals 2x plus y. So our dy dx when x is 0 and y is 1 is going to be dy dx equals 2 times 0 plus 1, so that's 1. So then to figure out our next y value, so our y when x is 1 will equal our previous y value plus our step, which is 1 times the derivative in the row before it. So 1 times 1. 1 plus 1 is 2. So the new y value is 2. So our dy dx at that point equals 2 times 1 plus 2, which is 4. So to get our y when x is 2, it's going to be our previous y value plus our step times the slope from the line before. So this is 2 plus 4, which is 6. So our y value is 6. We'll get our new slope. Dy dx equals 2 times 2 plus 6, which is 10. So that slope is 10. So our y when x is 3 equals our previous y plus our step times the slope from the line before. So that'll be 16. So that's one of our solutions. But then we need to keep going till x is 5. So we have dy dx equals 2 times x, which is 3, plus y, which is 16. So that'll equal 22. So the slope is 22. So our y when x is 4 equals our previous y value plus our step times the slope. So that gives us 38. Now we'll find the slope there. So we have dy dx equals 2 times x plus y, which equals 46. Now we'll find y when x is 5. which is the previous y value, plus our step times our slope. So 38 plus 46 is 84. So when x equals 3, y equals 16, and when x equals 5, y equals 84. So there's the solution to this question. So next we have separable differential equations. If the derivative can be split into a function of x multiplied by a function of y, then you can move everything with y to one side and everything with x to the other side and then integrate. So you would multiply both sides by d of x and divide both sides by g of y to get dy over g of y equals f of x dx. And then you could take the integral of both sides, as shown here, to find your solution, and then you would solve for y. So here we have our second IB practice question, which will use separable differential equations. So we have solve for y if dy dx equals xy plus 2x minus 3y minus 6. So we have 4 terms. So we're going to factor by grouping these 2 terms and these 2 terms. So our greatest common factor of the first 2 terms is x. So we'll have dy dx equals x times, and then what's left on the inside is y plus 2. And then our greatest common factor for the second 2 terms is negative 3. So we'll have negative 3, and then what's left on the inside is y plus 2. So since these are the same, we can factor that out. So we get dy dx equals y plus 2 times x minus 3. So we have a function of y times a function of x. So we'll multiply both sides by dx and divide both sides by our y plus 2. So we get dy over y plus 2 equals x minus 3 dx. Now we can integrate both sides. So the integral of 1 over y plus 2 is going to be the natural log of y plus 2, and that'll equal the integral of x minus 3, which would be 1/2 x squared minus 3x plus c. So now we want to solve for y. So we'll take e and raise it to the power of both sides. So e to the natural log, those will cancel and you'll just have y plus 2 equals e to the 1/2 x squared minus 3x plus c. And then we'll subtract 2 from both sides to get y. So we have y equals e to the 1/2 x squared minus 3x plus c minus 2. This plus c up here, we can separate this into y equals e to the 1/2 x squared minus 3x times e to the c minus 2, and e to some constant will just equal another constant. So we could say y equals some constant, c1, times e to the 1/2 x squared minus 3x minus 2. So c1 equals e to some constant. So our solution is that y equals c1 e to the 1/2 x squared minus 3x minus 2. The next method we have for integration is substitution for homogeneous differential equations. So if the derivative can be written as dy dx equals f of y over x, then you'll substitute in v equals y over x, which can be solved for y, where y equals v times x. Then you'll take the derivative of y equals v times x, which is dy dx equals x times dv dx plus v. Then you'll substitute those values into the differential equation. So we had dy dx equals f of y over x. So we found that dy dx equals this here, and then we substituted v for y over x. So we end up with this equation, which will integrate, And then after we do the integral, we'll need to resubstitute back in that v equals y over x. So here we have our third IB practice question where we're going to use substitution for homogeneous differential equations. So we need to rearrange this equation to just have dy dx on this side. So dy dx equals 3xy plus 4y squared all over 2x squared, because we divided by that. Then we can split this into two fractions. So we have 3xy over 2x squared plus 4y squared over 2x squared. Then we can simplify. We can cross out an x here and in the denominator. And we can simplify the 4 and 2 to be 2 and 1. So we have 3y over 2x plus 2y squared over x squared, which if we pull the constants in front of the variables, we have 3 over 2 times y over x plus 2 times y squared over x squared, which is y over x squared. So dy dx equals 3 over 2 times y over x plus 2 times y over x squared. So we can substitute v for y over x, which when you solve that for y, that means that y equals x times v. And the derivative of that, using your product rule, will give you x dv dx plus v. So we can substitute this into the equation here. So dy dx equals x dv dx plus v. And that equals 3 over 2 times v plus 2v squared. So we can subtract v from both sides. So we get x dv dx equals 3/2 v minus v is 1/2 v plus 2v squared. So to get rid of our fraction here, we'll multiply both sides by 2. So we have 2x dv dx equals v plus 4v squared. Then we want to get all of our x's on one side and our v's on the other. So we'll divide both sides by 2x and we'll divide both sides by v plus 4v squared. So that'll give us 1 over v plus 4v squared dv dx equals 1 over 2x. So then we just multiply both sides by dx to get that 1 over v plus 4v squared dv equals 1 over 2x dx. So we can't take the integral here yet. So what we're going to do is we're going to split our 1 over v plus 4v squared using partial fractions. So this is equal to 1 over v times 1 plus 4v. So we have 1 over v times 1 plus 4v equals a over v plus b over 1 plus 4v. So we'll multiply everything times v times 1 plus 4v. So that gives us that 1 equals a times 1 plus 4v plus b times v. So if v equals 0, then we have 1 equals a times 1 plus 0 plus b times 0. So 1 equals a. So we have 1 equals a, which is 1, times 1 plus 4v plus b times v. So if v equals any other number, so we'll try 1 for example. So if v equals 1, we have 1 equals 1 times 1 plus 4 plus b. So that means 1 equals 5 plus b. So we'll subtract 5 from both sides to get that negative 4 equals b. So now this is equal to the integral of a over v, so 1 over v dv, plus the integral of b, so negative 4 over 1 plus 4v dv, and that equals the integral of 1 over 2x dx. So the integral of 1 over v dv is the natural log of v, plus we can pull our negative 4 out front, so we have negative 4 times the integral of 1 over 1 plus 4v is the natural log of 1 plus 4v. And then we need to do the reverse chain rule. So instead of multiplying by 4, we're going to divide by 4. And that'll equal the natural log of 2x, and then we have plus c. So this simplifies to negative 1. So since we have the natural log of something minus the natural log of another thing, we can combine them to be the natural log of v over 1 plus 4v, and that equals the natural log of 2x plus c. We'll do e to the power of both sides. So this e and natural log will cancel. So we have v over 1 plus 4v equals e to the natural log of 2x times e to the c. E to the natural log of 2x just becomes 2x, and e to the c can just equal another constant, which we'll call c1. So we can come up this way and say v over 1 plus 4v equals c1 times 2x. c1 times 2 can equal another constant, so we can say c sub 2 equals c1 times 2. And then we'll solve for v by multiplying both sides by this denominator. So we'll have v equals c2x times 1 plus 4v. So we have v equals c2x plus 4c2xv. Then we'll subtract this term to the other side. So we have v minus 4c2xv equals c2x. We can factor out a v to get v times 1 minus 4c2x equals c2x. So v equals c2x over 1 minus 4c2x. And then we know v equals y over x. So we have y over x equals c2x over 1 minus 4 times c2x. Then to solve for y, we'll multiply both sides by x. So we get y equals c2x squared over 1 minus, and then we can say 4c2 is another constant, c3. So c3x. So this here would be our solution for y. Finally, we have our integrating factor. So this is a method for solving differential equations in the form of y prime plus some function times y equals another function. So once you have it in the form above, the integrating factor, mu, will be equal to e to the integral of p of x dx. You'll multiply every term by that integrating factor, and then simplify both sides to get d dx of the integrating factor times y equals the integrating factor times q of x. You'll then integrate to get that the integrating factor times y equals the integral of the integrating factor times q of x dx, and you'll solve for y. So here we have a practice question using the integrating factor. It says, solve for y if dy dx plus 3x squared times y equals x squared. So this is our y prime plus p of x times y equals q of x. So our p of x is this here. So our integrating factor equals e to the integral of 3x squared dx. So this equals e to the x cubed. So now we're going to go ahead and multiply that by all of the terms. So we have e to the x cubed times dy dx plus e to the x cubed times 3x squared y equals e to the x cubed times x squared. So this simplifies to d dx of e to the x cubed times y, because if we did the derivative of e to the x cubed times y, we would get the derivative of the first, which would be 3x squared times ex cubed dx dx, which is 1, times y, plus the first, e to the x cubed, times the derivative of the second, which would just be dy dx. So this here is the same as this, which is why we can make the jump to here. So we have d dx of e to the x cubed times y equals x squared times e to the x cubed. So we'll multiply by dx. So we get d e to the x cubed y equals x squared e to the x cubed dx. So if we take the integral of both sides, this just becomes e to the x cubed times y equals the integral of this. We'll use u substitution, so we have the integral of x squared e to the x cubed dx, and we'll say that u equals x cubed, so du equals 2x squared. So we'll need a 1/2 out here to get a 2 in there. So we'll have 1/2 times the integral of e to the u du, which equals 1/2 e to the u plus c. So this is 1/2 e to the x cubed plus c. So this equals 1/2 e to the x cubed plus c. So if we divide both sides by e to the x cubed, we get that y equals 1/2 e to the x cubed over e to the x cubed is 1/2 plus c times e to the negative x cubed. So this would be our solution to this problem. So in summary, Euler's method is a method for approximating the solution to differential equations when given a derivative and an initial value. Separable differential equations are if the derivative can be split into a function of x multiplied by a function of y, then you move everything with y to one side and everything with x to the other side and then integrate. For substitution for homogeneous differential equations, if the derivative can be written as dy dx equals f of y over x, then you substitute v equals y over x to make it possible to find the solution. And an integrating factor is a method for solving differential equations in the form of y prime plus p of x times y equals q of x by multiplying every term by the integrating factor e to the integral of p of x dx. That's all for this video. Thank you for watching.